Hello everyone, welcome to BHARGAV SUBS. So in today's class, let us discuss a concept regarding what is the correction made by Maxwell from Ampere's law. Okay, Maxwell did a correction. Like initially, Ampere gave a equation which regards magnetic field. Okay, there is a magnetic field in the length L, right? So that was equal to that is directly proportional to the charge current enclosed in that loop. Okay, originally Ampere's law, what Ampere's law says, what Ampere law says, closed integral magnetic field in the length dl is equal to mu naught into I enclosed. Okay, this was the equation given by Ampere, right? So what does it means? Like B is directly proportional to the current enclosed. But see, like he didn't consider, like he only considered for steady currents. Okay, what Ampere did the mistake, he only considered for steady currents, but he didn't consider like displacement currents. Okay, what is the current electric field changing with the time? Okay, the time varying field he didn't consider. Okay, it's not valid. This equation not valid for time varying fields. For example, I am taking a capacitor in which the current was flowing. See, conduction current. See, I took a capacitor and here I applied like external circuit. So in this the current was flowing. Here the current was not flowing. Okay, there is no conduction here. No conduction current. Okay, there is no conduction current. So if I according to Ampere law, if I applied this law to this loop, I will get zero. Okay, zero current. But see, there is a current is carrying inside the wires. Okay, there is a current carrying like outside the capacitor, excluding capacitor. The current was flowing here. The current was flowing in the wires. So he didn't consider this current. Okay, he only considered where the, like it is a dielectric. Okay, in dielectric there is no current flows, right? So in this, like he only considered steady currents. He didn't consider the current which was flowing or the current or the electric field which is varying with time, right? So what is the displacement? That is known as displacement current. The current was displaying. What is displacement current? ID is equal to epsilon naught dE by dt. Okay, the electric field was varying with time. So he didn't consider this displacement current. After considering displacement current, what I will get in enclosed? So B dot dl is equal to mu naught into, I am adding like steady current I enclosed plus what is it, like epsilon naught dE by dt, right? So after applying like Maxwell equation, I will get this form. So I have Maxwell did a correction like adding the displacement current. Okay, adding the displacement current. He applied displacement current. So this was the correction made. Like this was the Ampere law. This was the Maxwell's law, right? So before there was equations like before Maxwell and after Maxwell. Okay, before Maxwell, after Maxwell, there was equation in that Ampere law which was there. Initially there is no displacement current in that, but after that they added a displacement current. So there is a change in the Ampere's law. So we will discuss like how he was changed the value, how he was added the displacement current, right? So let us do it by step by step. So generally Ampere's law is not valid for time varying fields, like in which that current is changing with time. Okay, the field was changing with time. He didn't apply it, right? So what is it called? Ampere's law, like initially Ampere law is not valid for time varying fields, right? Not valid for time varying fields. Okay, so there is, I told you conduction current. Conduction current is not only a source of magnetic field, but also it is a source of electric field. Okay, so conduction current is not only a source of not only a source of magnetic field, but also it is a source of, it is due to electric field. Okay, it is like as this also a source of magnetic field, as it is a source of magnetic field, right? And so as it is a source of magnetic field, and also like it is equal to the current which is known as displacement current. So which is equal to current known as displacement current, right? Displacement current. So therefore, hence for like the field which was varying with time, there is a modification required. Okay, so hence time varying fields requires modification. So this was the like Ampere law is generally not valid for time vary field initially. So after Maxwell came, like conduction, he declared that conduction current which was flowing is not only due to magnetic field but also due to change in electric field. Okay, changing. So it is due to changing electric field, as it is a source of magnetic field. Like rate of change of magnetic field will give rate of change of electric field will give magnetic field. Okay, so like changing magnetic field, as it is a source of magnetic field. Okay, so it gives so like changing electric field as it gives magnetic field, which is equal to the current. Okay, displacement current, there was a current displaced in it. So like we require a modification. So let us do that modification. For modification, what we have to do? So let us do that modification for Ampere's law. Okay, Ampere's law. So what is the let us do the modification. So I have to take equation of continuity. In previous video I discussed like equation of continuity. Consider equation of continuity of current. Like it is a basic general equation like in which we will consider. So gradient of J is equal to, what is it called, minus d by dt of charge density, right? So actually it was like plus d rho v by dt is equal to 0. After transferring that, J is equal to minus d rho v by dt. Yeah, now this was the first equation. Okay, now what I have to consider? Now I have to consider what is it called, Gauss law, right? So now I have to consider Gauss law. So then I have to substitute there. What is Gauss law? Like gradient of electric field is equal to rho by epsilon naught. So from Gauss law, what the Gauss law theorem says? From Gauss theorem, what it says? Gradient of gradient dot electric field is equal to rho by epsilon naught. Okay, then what is rho? Epsilon naught into gradient of E. So this was the equation 2, right? Now I am substituting 2 in first equation, right? So 2 in equation 1. So what I will get? Gradient of J is equal to minus d by dt of rho v means like epsilon naught gradient of E, right? So J is equal to, gradient of J is equal to minus d by dt gradient epsilon naught E. So this epsilon like gradient will get cancelled. So what I will get finally? J is equal to minus epsilon naught dE by dt. So I got this, right? So I got J is equal to minus epsilon naught dE by dt. So like this is also known as displacement current density, because rate of change of electric field, like rate of change of electric field, it will gives the current, which is known as displacement, like current density. Okay, rate of change of electric field will gives current density. Okay, current density which is displaced. Okay, which this was displaced. So J displaced is equal to minus epsilon naught dE by dt, right? So this was the third equation. Now we have to come out the Ampere law. So what was Ampere law? What was the Ampere law originally? Ampere law is gradient cross B is equal to epsilon naught, like mu into J, right? J net, right? So gradient cross B is equal to mu into J net, means J free minus J displacement, right? So gradient cross B is equal to mu into J free minus J, what is J displacement, minus epsilon naught dE by dt. So finally I will get gradient cross B is equal to mu into J free plus epsilon naught dE by dt. So if I multiply with mu, what I will get? Mu into J free, mu into J plus mu epsilon naught dE by dt. So it was the modification made by the Maxwell for Ampere law. So not only due to the steady current, he says, not only due to the steady current, like current was flowing, no. So the output of like magnetic field is like gradient cross magnetic field is not only directly proportional to the current density which of steady, it also proportional to the current which was displaying. Okay, like displaced current. So the like rate of change of electric field also gives a magnetic field. So like it was a magnetic field, both are magnetic field, but it was with time varying field, like with time changing, the current flux was changing, like current flux is changing, no. So mu epsilon naught dE by dt. So like let us write equations what are before Maxwell's and after Maxwell's. So before Maxwell's equations, what are the before Maxwell's? First one, gradient dot E is equal to rho by epsilon naught. Okay, so second one, what is second one? Gradient dot B is equal to 0, right? Third one, gradient cross E is equal to minus rate of change of magnetic field. Fourth one, gradient cross B is equal to mu J. So this was the before Maxwell's. So now after Maxwell's, what we got? After Maxwell, so first one same, gradient dot E is equal to rho by epsilon naught. Second one same, gradient dot B is equal to 0. Third one same, gradient cross E is equal to minus rho B by rho T. So fourth one changes, so gradient cross B is equal to mu J plus mu epsilon naught dE by dt. So this was the change by Maxwell, like for this was Ampere's law. Okay, this was Ampere's law. So like this was Gauss law, right? These were the Gauss laws, this was Ampere's law. So this was changed by Maxwell. So finally I got the change in magnetic field, like that's it. Like he considered only current density of steady current. So after came Maxwell, he also considered time varying field. Okay, initially Ampere Ampere law says it was not valid for steady, like not valid for time varying fields, right? So like then what he says, there is a conduction current which is not only due to the magnetic field but also it is due to the changing in electric field. Okay, changing in electric field will gives the magnetic field, like changing in electric flux will gives the generation of magnetic field, correct? So finally he came across that and he considered like equation of continuity, right? Equation of continuity, and then substituted. What was that equation? Like in equation of continuity, he substituted that Gauss law, right? After substituting Gauss law, he applied Ampere law. Like he took Ampere law, J net. He applied not only J free, but also there is a displacement current density. So from Gauss law, after substituting Gauss law, you will get this displacement J, right? So because rate of change of electronegativity will give the displacement current density. So this was substituted. After substituted, we got that J is equal to J is equal to, what is it called? Finally, del cross B is equal to mu J plus mu epsilon naught dE by dt. Okay, so before, after. Yeah, this was the correction did by what you call Maxwell for Ampere's law. Okay, this was correction of Maxwell for Ampere's law. Yeah, that's it. Thank you.